Overview of CUDA. What is CUDA? CUDA, which stands for Compute Unified Device Architecture, is a parallel computing platform created by NVIDIA. It allows developers to use the GPU for general-purpose computing instead of only graphics processing. CUDA is based on C and C++ programming languages and provides an API that supports parallel execution. By running thousands of tasks at the same time, CUDA significantly improves performance and speed. It is widely used for tasks such as matrix calculations, linear algebra, image processing, and scientific computing. Why do we need CUDA? First, massive parallelism. While CPUs have only a few powerful cores, GPUs contain thousands of smaller cores. CUDA allows us to use these GPU cores to perform many computations at the same time. Second, high throughput for data-intensive tasks. CUDA processes large datasets much faster than traditional CPUs. It is widely used in applications such as matrix multiplication, artificial intelligence training, and video processing. Third, performance boost. Tasks that may take minutes on a CPU can often be completed in seconds on a GPU. In suitable parallel workloads, speedups of 30 to 100 times are common. Finally, general-purpose GPU computing. GPUs were originally designed for graphics, but CUDA enables them to perform general computations, including scientific simulations. At the top is the host CPU, which manages the overall program and controls execution. When a parallel task is required, the CPU launches a kernel and sends it to the GPU device. The GPU device receives this kernel and is designed to handle massive parallel computations. Inside the GPU, the workload is distributed across multiple streaming multiprocessors, such as SM1, SM2, and SM3. All these streaming multiprocessors access a common global memory, which stores input data and computation results. Each streaming multiprocessor contains a warp scheduler, responsible for scheduling groups of threads efficiently. The actual processing is done by multiple CUDA cores, which execute instructions in parallel. Each SM uses registers to store private data for individual threads. It also uses shared memory, allowing fast data sharing among threads within the same SM. This slide explains the main components in the CUDA architecture. The host, or CPU, is where the main program begins execution. It controls the overall flow of the application and manages all GPU operations. The device, or GPU, performs parallel computation by executing thousands of threads simultaneously. A kernel is a function written in CUDA that runs on the GPU. It is executed by multiple threads in parallel. A streaming multiprocessor, or SM, is a processing unit inside the GPU. It manages and executes thread blocks. CUDA cores are the computation units inside each SM. They execute instructions for individual threads. Finally, CUDA uses a memory hierarchy that includes registers, shared memory, and global memory to optimize performance. This slide explains the CUDA program execution flow. The program starts on the host, which is the CPU. The application begins execution on the CPU, where input data is prepared and the overall execution sequence is controlled. Next, memory allocation is performed on the GPU. The CPU allocates memory on the device and transfers input data from host memory to device memory. After memory allocation, the CPU launches the CUDA kernel. During the kernel launch, the execution configuration is specified, including grid and block dimensions. The kernel execution is then organized into a grid of blocks. Each block consists of multiple threads that execute in parallel. Finally, thread blocks are assigned to available streaming multiprocessors. These SMs execute the blocks in parallel to achieve high performance. Now, the thread execution phase begins. Each thread executes the same kernel code, but works on different portions of the input data, enabling data parallel execution. Next is warp scheduling. Threads are grouped into warps of 32 threads by the warp scheduler. The scheduler selects warps and issues instructions so that threads execute efficiently in parallel. During memory access, threads use different types of memory. Registers are used for temporary variables, shared memory enables fast communication between threads, and global memory is used for large data storage. Efficient memory usage significantly improves execution speed. Finally, in result transfer to host, after kernel execution completes on the GPU, the computed results are copied back from device memory to host memory. The CPU then continues program execution using these results. Typical CUDA program flow. A typical CUDA program follows a clear sequence that shows how the CPU and GPU work together. First, the program starts on the CPU, which is also called the host. The host allocates memory on the system RAM to store input and output data. Next, the host allocates memory on the GPU, which is called device memory. After memory allocation, data is copied from the host to the device. Once the data is ready on the GPU, the host launches the CUDA kernel. The kernel executes in parallel on the GPU, using thousands of threads. After kernel execution finishes, the results are copied back from device to host. Finally, both host and device memory are freed, and the program ends. Typical CUDA program flow. Typical CUDA program flow begins on the host. Step 1. The program starts on the CPU, also called the host. The main control logic runs on the CPU. Host code is usually written using the C or C++ language. The CPU decides which part of the computation should be sent to the GPU. Step 2. Memory is allocated on the host. Input and output variables are created in system RAM. This memory stores the data that will later be sent to the GPU. Step 3. Memory is allocated on the device. The device refers to the GPU. Memory is created in the GPU's global memory. This memory will store the data needed for parallel computation. Step 4. Data is copied from host to device. Input data is transferred from the CPU to the GPU. This step makes the data available for execution inside the kernel. Step 5 is the kernel launch phase. In this step, the CPU instructs the GPU to start parallel computation. The CPU does not perform the computation itself. Instead, it launches a special function called a CUDA kernel on the GPU. While launching the kernel, the CPU specifies how many threads should execute the program in parallel. These threads are organized using a hierarchical structure. At the highest level is the grid. The grid represents the entire kernel execution. The grid is divided into multiple blocks. Each block is a group of threads that can cooperate with each other. Inside each block are threads. Threads are the smallest execution units, and each thread performs the same operation on different pieces of data. When the kernel launch instruction is issued, the GPU schedules all blocks and threads automatically. Each thread runs the kernel code simultaneously, allowing thousands of operations to be completed in parallel. This massive parallel execution is what makes CUDA programs very fast for large data computations. Step 6 is kernel execution on the device. After the kernel is launched, the GPU begins executing it internally. Each thread handles a small portion of the data. Instead of one CPU core processing everything, thousands of GPU threads work simultaneously. These threads do not run randomly. They execute on hardware units called streaming multiprocessors, also known as SMs. Inside each SM, threads are grouped into units called warps. A warp consists of exactly 32 threads. All threads in a warp execute the same instruction at the same time, but on different data values. Inside the kernel, Each thread calculates its own unique index. This index tells the thread which position of the data it is responsible for processing. Using this index, each thread accesses one element from the first input array and one element from the second input array. The thread then performs the computation, which in this case is addition. The result of this addition is stored in the corresponding position of the output array. Because thousands of threads perform this operation at the same time, the computation finishes much faster than a serial CPU execution. Step 7 is copying results from device to host. After the GPU finishes computation, the output data remains in GPU memory. The CPU cannot directly use this data, so the results are transferred from the GPU back to the CPU. This copy operation moves the final output from device memory into host memory, making it accessible to the main program. Step 8 is freeing memory resources. Once the data transfer is complete, the GPU memory that was allocated earlier is no longer needed. The program releases all device memory to avoid memory leaks. Host memory can also be released if it is no longer required. This step ensures efficient use of memory and keeps the system stable. Step 9 marks the end of the program. The program continues execution on the CPU. The CPU now uses, displays, or stores the final result. After this, the program terminates normally. CUDA limitations. Vendor lock-in. CUDA works only on NVIDIA GPUs. It cannot run on GPUs from other vendors. Complex memory management. Programmers must manually transfer data between CPU memory and GPU memory. This increases program complexity. CUDA is not suitable for all tasks. Programs with sequential execution or very little parallelism do not benefit from CUDA. Hardware dependency. A system must have a CUDA-capable NVIDIA GPU to run CUDA programs. Debugging difficulty. Debugging GPU code is more challenging than debugging CPU code. Finally, there is a learning curve. CUDA programming requires a strong understanding of parallel programming concepts. CUDA is used in many areas. It speeds up machine learning and deep learning tasks. It helps with image and video processing, like filtering and streaming. CUDA supports scientific simulations, such as weather forecasting. It also boosts data mining and big data analysis. And it improves medical imaging like MRI and CT scans.